Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. Suppose I want to walk out of this room through a door that is 10 feet away. My first step covers half the distance, taking me 5 feet forward. My next step covers half of the remaining distance, taking me another 2.5 feet. If I keep repeating this process forever, taking an infinite number of steps with each step covering half the remaining distance, will I ever actually leave the room? Or will I be trapped inside forever adding numbers for eternity? This is the famous Zeno's paradox, and the mathematical answer defies basic human intuition. Adding an infinite list of numbers together can actually equal a completely clean finite number. Welcome to the mind-bending world of infinite geometric series. Now before we jump in, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. An infinite geometric series keeps adding terms forever, but it will only add up to a fixed target value if the terms are shrinking down towards zero. We call this a convergent series. This convergence only happens under one strict restriction, and that is the magnitude of your common ratio must be strictly less than 1. If your ratio violates this rule, the numbers explode towards infinity and the series diverges. So the formula for an infinite geometric series is S sub infinity is equal to the first term divided by 1 minus the common ratio. So here, the magnitude of the common ratio is strictly less than 1, which means that r must be strictly between -1 and 1. So before you get excited and start using this formula everywhere, remember that the first step is always to check that the common ratio has a magnitude that is strictly less than 1. So now let's take a look at our first example. We want to determine if the infinite geometric series here converges, and if it does, we want to calculate its exact sum. So to check whether or not this series converges, we need to find what our r is. And r here is equal to 4 divided by 12, which is equal to 1/3. Now the absolute value of r is the absolute value of 1/3, so that's equal to 1/3, which is less than 1, which means that our series does converge. So now that this condition is satisfied, we can use the formula to find the infinite sum. So we get S sub infinity is equal to the first term, which is 12, divided by 1 minus the common ratio, which is 1/3. So this is equal to 12 over 2/3. And this evaluates to 18. So therefore, the sum of this infinite geometric series is equal to 18. Now let's take a look at our next example. We're told that there's an infinite geometric series where the first term is 45, and we know that the infinite sum is equal to 27, and we're asked to find the common ratio r. So all we need to do is substitute the values that we have been given into the formula. So we know that S sub infinity is u1 over 1 minus r, which means we get 27 is equal to 45 over 1 minus r. Moving 1 minus r over to the other side, we get 1 minus r is equal to 45 over 27, which simplifies to 5/3. So therefore, r is equal to 1 minus 5/3, which is -2/3. So our common ratio here is -2/3. And now for our last example, we're going to work with something a little bit trickier. We're told that an infinite geometric series has a first term that is equal to 8, and the common ratio r is equal to the expression that you see on the screen here. We're asked to determine the complete range of values for x for which the infinite series converges. So we know that convergence happens when the absolute value of r is less than 1, or in other words, r must be strictly between -1 and +1. So this means all we need to do is substitute the expression for r into this inequality here. So we get 2x squared minus 5x is greater than -1, but also less than 1, which means we have two inequalities that we need to solve. The first one being 2x squared minus 5x is greater than -1. which then we can move the -1 over to the left side, which means we get 2x squared minus 5x plus 1 is greater than 0. And then our second inequality is going to be 2x squared minus 5x is less than 1. Same thing, moving the 1 over to the left side gives us 2x squared minus 5x minus 1 is less than 0. So since both of these have a positive leading coefficient, they're both upward-facing parabolas, which means for the first one, it's going to look like this, and then all we need to do is find where the zeros are, and then the parts of the parabola that are greater than 0 are going to be the outside. And as for the second one, because it's also an upward-facing parabola, but this time we want the part where it's less than 0, which means it's going to be the part that is in between. So now all we need to do is use the quadratic formula to find our critical boundaries, or aka the roots of both of these inequalities. So for the first one, we would get x is equal to negative b, so that'll be positive 5, plus or minus the square root of 5 squared, which is 25, minus 4 times 2 times 1, so that'll be 8, over 2 times a, so that's going to be 4. So we get this is equal to 5 plus or minus the square root of 17 over 4, which means we would have x is less than 5 minus root 17 over 4, or x is greater than 5 plus root 17 over 4. And then for the second parabola, we would get x is equal to 5 plus or minus the square root of 25 plus 8 over 4. So this would be 5 plus or minus the square root of 33 over 4. So this means we get x is greater than 5 minus root 33 over 4, but less than 5 plus root 33 over 4. So since we need this to be true, it means we need to find values for x that can satisfy both of these conditions. And the easiest way to do that would be through a number line. So if we draw our number line, and then we plot our points, so the smallest value here is going to be 5 minus root 33 over 4. The next one is going to be 5 minus root 17 over 4. And then we have 5 plus root 17 over 4. And then the largest value here is going to be 5 plus root 33 over 4. So now from the first parabola, we need x to be less than 5 minus root 17 over 4. So that would be this direction here. Or x can be greater than 5 plus root 17 over 4, which means it would be that direction there. And then from the second parabola, we need x to be in between 5 minus root 33 over 4 and 5 plus root 33 over 4, which means it's going to be right in between, right over here. So that tells us that the overlapping parts would be this interval here and this interval here. So finally, that means the values of x that will give us a convergent series is going to be x is an element of. So now remember that our inequality here doesn't include an equal sign, which means our endpoints are not included within the interval. So we're going to be using round brackets. So this would be going from 5 minus root 33 over 4 until 5 minus root 17 over 4. And then union with our second interval, which is 5 plus root 17 over 4 to 5 plus root 33 over 4. So this would be our final answer. And now let's do a recap of what we covered in this video. We saw that even though we're working with a series that has an infinite number of terms, the sum can settle on a precise finite destination value, provided that the successive terms steadily decay towards 0. And this convergence is strictly conditional. If your common ratio has an absolute magnitude that is equal to or greater than 1, then your calculation formula becomes completely invalid. So therefore, remember to always check that first. And lastly, in exam settings, treat your convergence constraint as a domain barrier so that you can lock down variable boundaries. And now it is your turn to give this a try. Can you find the solution to the problem on the screen here? Make sure to leave your answer in the comments below and let us know what other sequences and series topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.